Page 52, we're going to work with some of the double angle rules for sine and cosine. All right, so well, really cosine. It allows us to convert from powers of 2 to powers of 1. So let me just show you really quickly here. So we know that cosine, one of the double angle rules for cosine 2x is equal to, actually there's a couple of there's three of them, so I'll actually write them all down and I'll show you which ones are relevant in this case. So cosine squared minus sine squared, then we have 2 cosine squared x minus 1, and then 1 minus 2 sine squared x. Alright, so let me just grab one of them. Cosine 2x. They moved the copy on me, so it always takes a moment of hesitation. Always looking in the wrong place. Alright, so if I take this relation here and solve for the cosine squared, I'd be adding a 1 to both sides. So I'd have cosine 2x is equal to 2, oh, sorry, I forgot the plus 1. The whole reason I did this. Plus 1 is equal to 2 cosine squared x, and then divide out the 2. And so I'd have cosine squared x is equal to, and I would split up the fraction here because there's an understood 1 here. So 1/2 cosine 2x plus 1/2. All right. So if you look at that and compare it to what we have here, it's essentially the same thing. In fact, this relation is just, so this relation is just this one with the numerator reversed by the commutative property. All right, so we're in pretty good shape there. And what I'll do is I'll just pop this other variation of the rule up there with the printed version of it, because that's a useful variation of it. All right. So the same idea would hold true for the 1 minus 2 sine squared x. So I'd have cosine 2x, set it equal to 1 minus 2 sine squared x. And then I would solve for the sine squared of x. All right, so it's the same idea here. You see I'd subtract the 1, do it a little quicker this time. So cosine 2x minus 1 equals negative 2 sine squared x. Divide everything by negative 2, and you get sine squared x is equal to, if I divide everything by negative 2, negative cosine 2x plus 1 over 2. And then when you break it all apart, you get 1/2 minus 1/2 cosine 2x. All right, so it's another useful variation of the rule. These rules are very handy. I'm going to shrink this down so I don't steal too much space. Size. They're very handy because when you're trying to integrate something that involves a power of 2 for sine or cosine, if your Pythagorean identities don't work out, you need to do something. And so oftentimes this is the something. All right. Now it also works with any argument that exists. So for example, a 3x as opposed to an x. Right? So you just kind of think of this as x in a very general sense. So I'll just highlight all the x's here. All right. So it's just a matter of substituting. And in fact, what a lot of people will do is they'll rewrite the general rules. Instead of cosine squared x, they'll write cosine squared a, where a represents some kind of argument. But either way, it's fine. All right, so let me take you through an example. So sine squared 3x, I would use my sine squared rule. either variation of it doesn't really make a difference. I can tell you that in most cases, even if you start with this rule, you almost always end up can't speak today, end up with that rule, the one I just started. All right, so this one. So it really is just a matter of deciding which one you're more comfortable with, knowing that all roads lead to Rome in the end anyway. All right, so in this case, the x value is going to be 3x. So what I'm going to do is I'm just going to grab the cleaner one. 1/2 minus 1/2 cosine of 2 times the quote-unquote x, which will be 3x. All right, so that replaces this. So that's done. We'll clean it up in a minute, but that's that for that piece. Then, you know, an additional variation on the cosine one, for consistency, we could write it as 1/2 plus 1/2 cosine 2x. So 1/2 plus 1/2 cosine of 2 times the argument, which is a 3x again, and then we slap on a dx at the end. All right, so now we have our substitution. Now it's algebra and a little housekeeping. All right. Fortunately, it does appear to be a difference of perfect squares the way it's set up, or at least have that structure. So two binomials, same ingredients, just one's positive, one's negative. All right, so that's good. I am going to rewrite. So 1/2 minus 1/2 cosine 6x. And then the same deal, just with a plus. So then, distributing, I get 1/4. The outers and inners will cancel out. So I'm multiplying the first and the last. The last is going to give me a negative 1/4 cosine squared 6x. We're still integrating. I haven't finished the job here yet. Now we could convert this over by factoring out a 1/4. That would give us a 1 minus cosine squared 6x dx. Now this is kind of one of those things where it's like, is this a necessary step? I could make a substitution right here using this rule, or I can use a Pythagorean identity to make this sine squared of 6x and use this rule. All right, so it's really 6 of 1/2 dozen of the other, because it ultimately ends up being the same skill. It's just now I don't have to worry about maybe distributing a negative and then screwing that up, you know, typical me. So this is the one I'm going to use. I'll make the substitution here, 1/2 minus 1/2 cosine of 2 times the argument, which is 6x. All right, so again, just applying this rule. All right, so we're still not at the point, or we haven't gotten to the point where we have integrated yet. So I'm leaving the integral, I'm leaving the dx, and I'm leaving the 1/4. Right? I can actually distribute the 1/4 because I don't think it's going to make things any more complicated. So that's what I'll do. And I'm also going to multiply the 2 by the 6x and get 12x. Now when I integrate, I'm going to get 1 over 8x minus, I got the 1 over 8, cosine becomes a negative, cosine becomes positive sine. We have sine of 12x, and because the argument here is linear, we just have to correct for it by multiplying by the reciprocal. All right, plus c, and that should be our indefinite integral. All right, I could clean it up just a smidge more. 1 over 8x minus 1 over 96 sine 12x plus c, and that should be it. All right, So I'm going to do a quick double check. Let's see, I have this from a different problem. 1 over 8 x minus 1 over 96. Different but similar, obviously. Otherwise, I wouldn't have so many changes. This is probably going to have to be changed. All right, well, anyway, let me explain what I'm doing here. So you type in your integrand, your integral, your final answer. Then tell the calculator to take the derivative of it. So actually, let me just do that step again. So I typed in the original function. I type in our answer as the original function. I'll get that right eventually. Math 8 brings up derivative. The variable is x. We want the derivative of y1 for all values of x. All right, so then what I would do is turn off my first equation because I don't want to see that, and just make sure everything else is the way it should be. We don't bother with the plus c because it could be any constant. So then what I do is I have the calculator take the derivative of this. In theory, that should be the same thing as sine squared 3x cosine squared 3x. So I'm going to type in sine of 3x. I go a little crazy with the parentheses, sine 3x quantity squared. I do it that way just so I know that I'm not going to get in trouble with the calculator misunderstanding what I'm trying or what my intention is. All right, so hopefully it's in correctly. It should be. Then I'm going to go to table and verify that my y2, y3s match up. All right, you might see some slight differences because it's doing it numerically, the derivative. So there's 3e to the negative 6. That's the calculator trying to say 0. It just never quite got there. Some people like the appearance, you know, the view of it. Let me do no, that's not a good one either. I'll start with a zoom 7, and then I'll correct for it. Let's see, we don't need negative 4 to 4. Negative 1 to 1 will do the trick. And we don't need to go out to negative short of 2 pi. Let's go to negative pi. Just to see. All right. We don't have two unique graphs. It implies that one is being graphed on top of the other, but what we can do to really emphasize that is make the second one bold so it really pops out at us. All right, and so there you go. All right. So that was number 3. Number 4, you can see cosine to the 4th of x. We could write that as cosine squared x times cosine squared x, which in turn would become 1/2 plus 1/2 cosine 2x times itself. All right, so again, all I'm doing is applying a rule. But then when I distribute, I get 1/4. I don't get that nice cancellation like the difference of perfect squares. The outers are going to give me 1/4 x. I'm sorry, 1/4 cosine 2x. The inners are going to give me 1/4 cosine 2x. So 2/4 cosine 2x, so 1/2 cosine 2x plus 1/4 cosine squared 2x dx. So we're going to have to apply the rule again to get us this piece. Alright, so I'm going to make the substitution there. Let me just pull this out for a sec. The argument is 2x, so I'm going to do a 1/2 plus 1/2 cosine of 2 times 2x. Then I bring my dx back in. Alright, so a little bit of algebra. So I have a 1/8 plus 1/8 cosine 4x dx. I got some like terms. So 1/4 plus 1/8, so that's 2/8 plus 1/8 is 3/8, plus 1/2 cosine 2x, plus 1/8 cosine 4x. Integrate 3/8 x, plus the 1/2. We're going to divide by the coefficient of x, so times another 1/2. Sine of 2x, because the antiderivative of cosine is sine. Alright, 1/8 multiplied by the coefficient of x's reciprocal, which is 1/4, times the sine of 4x plus c. Then it's just cleaning it up. And that's it.